Hello, my name is Danny Faulkner. I'm an astronomer. I received my PhD from Indiana University. For 26 and a half years, I was on the faculty at the University of South Carolina, Lancaster, where I taught astronomy and physics. Upon my retirement from the university, I spent 12 and a half years as a staff astronomer at Answers in Genesis. Over the years, I've published a few hundred articles in the astronomy literature, scientific literature. I've also published numerous articles in the creationary literature dealing with astronomy for the most part. I've also published 7 books dealing with creation and astronomy. I've also co-authored 2 other books as well. And I frequently like to speak about astronomical issues dealing with creation. It's my passion. Today I want to talk about design in astronomy. Design is something I've thought about and wrestled with for many, many years. I think it's obvious in biological systems, not so obvious in physical systems such as we encounter in astronomy. Yet, as a creationist, I would expect design to be around us. And I've tried to work on a definition that will work, but I just want to illustrate a few things today about astronomy that I think indicate design. And you know, there are really 2 explanations of how we and the world came to be. Now, one of them is going to be naturalistic. There is no God, there is no creator, or if he exists, he's not very relevant to things. And for lack of a better term, perhaps, I'm going to call that evolution. It's simply a purely natural, purely physical process. Yeah, I know biologists might argue about this and say, that's not the definition of evolution, but that's in biology. You see, evolution is not just a biology thing. It's in geology, it's in astronomy, it's in cosmology, it's also in law, sociology, history. Evolution's all-pervading idea. So I want to make it as broadly defined as possible. And I would say it's just simply a purely natural, purely physical process to explain how we and the world came into existence. Contrast to that is creation, which I'm going to try to define broadly as well. Creation is a supernatural process. Notice that I've not technically identified who the agent or what the agent is of that. So I want to make it very clear. I'm talking about the God of the Bible. I believe the scriptures tell us a lot about the creation. Not everything we might like to know, but enough that we need to know that we can build creation models around that. And you may ask, well, is it really important what we believe about this? I mean, after all, as long as we love Jesus, is that good enough? Well, I think it is important because, you see, it colors how we look at the world. I'm talking about your philosophy, your worldview. It's a lens by which we interpret the world around us. All of us have lenses we use, put on glasses, and they help us interpret the world. And those starting assumptions will lead to certain conclusions. If I know what your assumptions are, I can usually anticipate where you're going to end up on certain key issues. You see, we have 2 different ways of doing things. The creationist tends to see design and purpose in everything in the world around us, because there must be design and purpose if there is a creator. We may not know what that purpose or design always is, but we can be certain it's there. And many times I can recognize design, but I may not know why there is design there. And that's a key part of trying to identify design, is to find the purpose if we can. On the other hand, evolutionists don't see that. In biology, they see struggle. They see going on between organisms. Also, chance is there. Nothing's really planned, nothing's ordained, things just happen. So there's no design, there's no purpose in any of this. And it's again because we start with 2 very different assumptions. I begin with the assumption of theism, that there is a God, and more specifically that God reveals himself through Scripture. And also there is atheism. Atheism is a belief that there is no God, or perhaps you could say more of an agnostic. He doesn't really matter if he does exist. Now I want to illustrate that with 3 photographs I want to share with you. One of the neat things about astronomy is that it's just a beautiful thing. The images you might see taken with large telescopes or spacecraft are incredible. And if you ever have a chance to look at some of these objects through a large telescope particularly, you can be really impressed with what you see. But you're not going to see what the camera always sees, because our eyes can only collect light for a fraction of a second. And many of those photos took many hours and hours of accumulated light gathering to get these images. But I think we can all be impressed with the beauty and wonder that we see, and I think that's one of the big hooks that astronomy has for us. This first one I want to show you is what we call the Horsehead Nebula. It's called that because you can see that famous silhouette shape of a horse head right there. Now, when we look at this, we see the beautiful colors, the beautiful wonder here, but if you know a lot about physics, as we astronomers do, we can see a lot more. And what we're seeing here is a large cloud of gas across most of the field of view there, and that gas is made mostly of hydrogen. And some of these hot blue stars here are ionizing the gases that we have there, and the electrons recombine with the hydrogen atoms and they give off this distinctive red color. We call this H alpha for hydrogen alpha. It's the first emission line, what we call the Balmer series. It's caused by a transition from an electron in the third orbit down to the second orbit of hydrogen atoms. Now, the lower half of the photograph may have some of that hydrogen gas as well, but it's being blocked by a large cloud of dust particles. Now, dust particles are very small, about the size of cigarette smoke particles. So they're nothing like household dust. Very tiny things. They're made largely of silicate rocks, a little bit of ices on top of those, and maybe some iron whiskers as well, little tiny elongated bits of iron. Now, it's blocking the light of more distant stars down below. So the stars you're seeing here are either our side, this side of that big dust cloud, or just inside of it. But up above, there's not so much dust. We can see stars in front of it and stars behind because the dust cloud really isn't present up there. Notice the density of stars down here. If you look at a patch down here, you just got a few stars. The same patch up here will have a lot more stars. That's because we're looking much more deeply into space over here because the dust particles are not there. Now, the blue glow down here is caused by these hot stars right here. They're just inside, on our side of this dust cloud. And as they are there, they scatter light off. Have you ever looked at cigarette smoke in bright light? It looks bluish. Same thing going on here because you see it's going to reflect or scatter off the shorter wavelength light, which is actually blue in color. This little appendage sticking up here has a horsehead shape. It's two-dimensional. It's actually three-dimensional, but what we see is two-dimensional. What shape it has in 3 dimensions, if we could see it, may not resemble a horse head at all. And many of my astronomy colleagues tell me that if they ever find the other half of that nebula, they'll name it after me. Okay, this next photograph is that of a comet. I forget the name of this comet right off the top of my head. See some stars in the background. And comet means hairy star. We get the word comb from that, same root, Latin word. And deep down inside, there's a little tiny nucleus inside of that head of the comet right there, the brightest part of the comet. And that nucleus is only a few miles across, and it consists of little tiny dust particles, like we saw before. And it also is held together in a matrix of ice, largely water ice, but also other types of ices like methane and ammonia and carbon dioxide and such. Now, the orbits that comets follow are really far from the sun. You get the sun here, the orbits of the planets are kind of circular, like they're nearly circular, but comet orbits are big ellipses. They come in like this and come down and back out again. They move very quickly when they're closest to the sun at a point we call perihelion, move very slowly out here. So they spend most of their time in the deep freeze of space far from the sun. But when they come once each orbit, they come rapidly around the sun at perihelion, so close to the sun, the radiation of the sun heats it up, causes those ices to sublime. They go directly from ice to gas. They expand rapidly into the space around it, forming the coma, or the head of that comet. And it's ionized gas now. It's being ionized by solar radiation, and that tends to cause the electrons to escape and come back and recombine, giving off visible light. So the coma gets very bright, but then solar wind and radiation push both the ion particles, the gas particles, and the dust particles that are dislodged away from the sun. So we know the sun is in this direction. The tail always points away from the sun, even though that may be the direction the comet's going. You see, the tail doesn't follow behind. It has a dust and an ion tail. You can see both of those there. Now, the third picture I want to show you is a very famous thing called the Ring Nebula. Through a good-sized telescope, it looks like a smoke ring. It won't be quite this colorful because our cones, our color-sensitive eyes, don't really pick up the colors very well until you get a lot of light. And we used to think this thing was like a bubble of gas. We now think that it's more like an hourglass. Got an hourglass like this, except we're not looking down the side of it, we're looking down the top or bottom of it, so it has this kind of a circular shape. And down in the center is a very hot, bright star. We believe that sometime in the past, the outer regions of the star were pushed off, blown off by stellar winds, which finally exposed the core of that star left behind, that very hot core, and now heading toward what we think is a white dwarf star. And the radiation from that ionizes the gas to give you that bright glow. And over time, that shell will expand outward. It'll get farther from the star will fade and get less hot. And eventually, this nebula will disappear into the interstellar medium, not to be seen again. All right, I've shown you three beautiful pictures. What did you see? Well, I think everybody would agree that you have beauty showing up there. That's, again, the wonder of astronomy, the wonderful things you see. Now, I went beyond that a little bit because I wanted to share with you some interesting physical processes. And see, physicists can see that, and as I went through that, you may have not followed much of that. That's fine. I was just trying to show you that there are a lot of things we can deduce about these things from studying science, which is an important thing that we creation scientists like to do. So you got the beauty and the wonder, and you've got the science there, the physics involved. But there's a third thing going on. And many people miss that. Everybody gets the first one. Some people get the first one and the second one, but a lot of people miss that third one because, you see, I have to think about Psalm 19:1. It shows the Creator's handiwork. And that's kind of been my life verse most of my life. It tells us that we have the heavens declare the glory of God, and the sky above proclaims His handiwork. As an astronomer, as a creationist, Bible believer, belief in Christ, I have to take this as my life verse. It's like the world around us, the astronomical realm, is like a giant billboard advertising God's existence. And go back to Romans 1:19 and 20, where it says two things. It says the world around it itself tells us two things. Number one, God exists, and number two, He's very powerful. Doesn't tell you everything else, but it tells you enough that you ought to start searching. So it says there that men are without excuse. Many times I will be driving along and I'll see a billboard, and sometimes I'll see an advertisement on television. My wife and I are watching TV, and I see this advertisement, and I have no idea what the TV advertisement's advertising. I have no idea what the billboard's advertising. If my wife was with me in the car or sitting in the living room with me at home, I turned to her and I said, "Do you know what they're selling? What the point of the ad is?" And my wife says, "I have no idea." And I think it may have something to do with their age. I like to tell young people, I think, I may be wrong, but I think I may have been cool once, but that was a half century ago. And a lot of the advertising is geared towards younger people than me. I really missed the point. And that's what's going on here. I think many people miss the point. God providing this knowledge that He exists and He's very powerful. And consequently, I think design is not a conclusive argument. Because you see, if one is convinced, like I am, and hopefully you are, that God exists, then you're going to be easy to see that design because you expect that design, because your worldview tells you there must be design because there is a designer of this world. On the other hand, if you don't believe that there's a creator, then you're going to tend to ignore that evidence, and you're going to minimize it, and you're going to pretend like it really didn't happen at all. So it's hard to convince the unconvincible on this front, on this whole front. Now, if you're one of those, all I'd ask you to do is please bear with me and listen, and maybe I can shake you from that position a little bit, maybe give you something to think about. And one of the best ways I can talk about that is with a total solar eclipse. I've been to totality 3 times. I'm kicking myself over the years that I didn't spend the money and go to other eclipses. It's kind of expensive to go to the eclipses many times because of where they may be in the world. This is one I took of the eclipse in 2017. I was in Oregon, east of the Cascades, and I used a Questar telescope, a 3.5-inch telescope. This is actually the actual, it's not been cropped, this is the actual size. You see the telescope has a 1,300 millimeter focal length. For those of you who know photography, you know that's a wonderful whale of a telephoto lens. And during totality, the sun's covered up, the photosphere is, and you see the outer corona, and I'm just getting the inner part of the corona right here because it extends out several diameters of the sun, and I can't possibly get it with this particular telescope. But I can get the inner part of the corona. It's a pearly white. It's extremely hot, on the order of 1,000,000 or 2 Kelvin temperature, so it's extremely hot. But on the edges, you have these little prominences, these little red loops on the edge of the sun. Now, if you want to photograph these things during eclipses, you need to take a short exposure to catch the prominences, like a 100th of a second, 60th of a second, and they show up nicely. If you want to get the corona, you got to go a second or two. And when you do that, you overexpose those prominences. But the eye responds very differently than cameras do. The eye allows you to see both the prominences and the corona in its full glory. That's because our eyes respond to light very differently. They respond logarithmically. They compress large differences in brightness. The camera responds linearly. So if you've seen photographs of eclipses and you think you've seen what an eclipse looks like, you have not, because the camera doesn't reproduce what we see with our eyes. I've seen totality, as I said, 3 times, and it is the most remarkable thing I have ever encountered. It's not just it gets dark and you see these things. There's so much going on around you, and many times you'll see videos of people shouting and cheering and carrying on. We had a young woman with us in 2024, and she was driven to tears. It was such a moving experience. I have a very different reaction. I shut up. I don't say anything because I'm so in the moment. I am just trying to drink in everything I possibly can. A friend of mine took this photograph in 2017. It shows it's a much smaller scale photograph, so you get the corona going far out, and you see these streamers inside the corona. Notice that those prominences, same place right here and right here, they're really overexposed and not showing up. But to the eye, you saw it all. And by the way, when totality comes, you take the eclipse glasses off. I know people both in 2017 and 2024 at the total solar eclipses, they were so afraid, they've been so told to wear the glasses, they left them on during totality. I'm sorry to say they lost it completely. You're supposed to take the glasses off and drink it in, but before totality ends, you put them back on if you're going to look up. And just for a brief instant before and after totality, there's this thing called the diamond ring effect. A first little bit of the sun returning, coming by through a little, maybe a crater wall, inside of a crater on the edge of the sun, the edge of the moon there. I took this photograph in 1979 with film, as a slide film, and we were able to scan this and make a digital image out of it. But I happen to like this photograph. It's really nice, and that is called the diamond ring effect, but you better not watch for it because it's extremely dangerous. Well, there's much design found in total solar eclipses. I like to call it the 400-400. What I mean by that is the sun is 400 times larger than the moon. Think about that, 400 times larger. So if you want to make a model of this, the moon might be 1 inch across, the Earth would be 4 inches across, and the sun would be 400 inches across. That's over 30 feet, something like that. However, the sun is 400 times farther away than the moon is. 400 times larger, but 400 times farther away. What that means is they both have about the same angular size, about a ½ degree in our sky. And so during a total solar eclipse, the moon just barely covers the sun. Barely does so. So with that barely coverage there, it does 2 things. Number one, it makes eclipses be spectacular. If the moon were a little smaller or a little farther away, we would never have any total solar eclipses. On the other hand, if the moon were a little larger or a little closer to us, it would be so large it would completely block and then some, in which case the eclipses wouldn't be very interesting because it would be what we say grossly over total. But it also means that eclipses are extremely rare. It turns out that across around the world, at any given location, it's about 4 centuries between one total solar eclipse to another. It may be thousands of years, but on average, it's only 400 years. For instance, in 2017 and 2024, those 2 eclipses across the United States, they crossed in southern Illinois, and there's an area there that got 2 eclipses just 7 years apart. But it may be thousands of years before they get to the next one. That means that if you want to see a total solar eclipse, you need to either be very lucky or you need to travel some distance to get there. I've had to travel each time. One time didn't have to travel too far, just a few hours, couple of hours. Now, there is a total solar eclipse somewhere in the world about every year and a half, but usually it's in the middle of the Pacific Ocean, the Antarctic, Siberia, who knows, different places like that. So again, you're either lucky or you plan ahead and travel to get there. Again, spectacular and rare. But you know, if you look at the other natural satellites, or if you will, moons of the other planets, and there are many, many of them out there, none of these circumstances are met on any of those. And this is the only planet where it matters, because it's the only planet where there are beings, you and me, capable of appreciating this fact. Now, you can say, well, that's just a coincidence. Just a coincidence that the moon and the sun have that 400-400, it gives you spectacular and rare total solar eclipses. But I have to ask you, how many coincidences are you allowed to have before you begin to realize that they are not coincidences at all? And this is just one of them. There are many others. Now, we have the moon, and there's design implied in the moon as well. For instance, the moon is large compared to the Earth. It's very large compared to the Earth. I'm talking here about the size, and not the size, the diameter, but the mass. Turns out the mass of the Earth is only 81 times that of the moon. That is, the moon's only about 1.3% the mass of the Earth. Now that may sound like a big mismatch. 81 to 1, that's a huge mismatch. But when you look at the other natural satellites or moons of the other planets, the mismatch is more like 12,000 or more to 1, 10,000, 1,000,000 to 1. In many respects, you could call the Earth and the moon a double planet. All right, so the moon is large compared to the Earth, and the moon's orbit around the Earth is unique. We all know that there's an orbital plane like this around the sun. The Earth goes around like this in this plane, but we all learned in grade school that the actual tilt, the axis of the Earth is tilted about 23.5 degrees, like that. So you've got the equator in this plane like this, and you've got the orbital plane around the sun like that. There's a 23.5 degree angle between those two planes. Now, many of the larger natural satellites in the solar system orbit in the equatorial plane above the equator like this. There's only one natural satellite that orbits close to the plane that the planet orbits around the sun. It's the Earth and the moon. Only the moon orbits in that kind of plane. None of the others do that. That's rare. So rare to be unique. Well, so what? Well, remember the tilt. You learned in grade school, the tilt determines the seasons. What they didn't tell you in grade school is that forces in the solar system, other planets in the sun, are yanking on the Earth's rotation axis, and over time, it will cause the rotation axis to have no tilt at all. Zero tilt. Now, what would happen if we had zero tilt? There would be no seasons. Same weather all the time. We have a very different regime on Earth with the plants. They would have to grow the same thing all the time, no seasonal changes at all. But hold on, that same forces would also cause that tilt to go to a much greater value, near 90 degrees. Now, if you get close to 90 degrees, much of the Earth's surface would simultaneously be in the tropics and in the Arctic or Antarctic. I think if you think about that for just a few minutes, you'll realize that's not good. Plants can't handle that. Animals can't handle that. It's nice that we have this kind of a moderate range, 23.5 degree tilt, so that part of the planet's in the Arctic or Antarctic, and animals and plants do okay there, but not elsewhere. And then you get the tropics where things do pretty well, and then you get the temperate levels in between. Turns out we have a nearly ideal tilt to it, but what would happen then if it changed? Because I said forces in the solar system are causing it to slowly change from 0 to 90 and back again. That would be catastrophic for living things, obviously. But it doesn't do that. Why? Because the moon acts as a stabilizer. It causes the tilt to be restricted, and so the tilt over time will only change by a couple degrees. It'll go back, say, to 23, 22.5, up to 24, and back. It'll wobble back and forth, but it won't get out of that narrow range of only a couple of degrees. Right now, the tilt is decreasing. It's becoming less and less. 100 years ago, it was 23.5. Now it's closer to 23.4. And so it's within a narrow range. Now, how does the moon do that? Well, it's kind of complicated, but two things are necessary. It must have a fairly large mass compared to the Earth, and it does. And it also must orbit in the, not in the equatorial plane, but in the, what we call the ecliptic plane, the plane of the Earth's orbit around the sun. And it does. Remember, it's the only planet, and it's the only natural satellite in the solar system that has both those characteristics. The right kind of orbital plane, no other satellite has, and the large mass, no other satellite has that. If it had one and not the other, it wouldn't work. Now again, you could argue, well, it's just a coincidence. In this case, not one, but two coincidences to stabilize life on Earth as we know it. Again, how many coincidences can you have before you realize that they're not coincidences? While we're talking about the moon, I like to point out that the moon, its existence, made physics as we know it possible. If you know anything about the history of physics, you know the author, the father, if you will, of physics as we know it was Isaac Newton, living 350 years ago. He wrote a book called the Principia. And in the Principia, he developed calculus, he developed his laws of motion, and most importantly, perhaps his law of gravity. That's foundational to physics as we know it. The law of gravity is an inverse square law. Inverse square meaning that you've got the distance between two bodies in the denominator and it's squared. These two masses are the mass of the body. So for instance, if we're talking about the moon orbiting around the Earth, which is, by the way, the problem that really was insightful for Newton, was able to do what he's able to do. The big M would be the mass of the Earth. The little m would be the mass of the moon. The distance here, r, would be the center-to-center distance, the distance from the center of the moon to the center of the Earth. And g is just the constant we put in to make the units work out appropriately. Its value depends on what units you're using. So, how did Newton figure this out? Well, his first and second law helped him realize that, and third law too, helped him realize the masses of both the moon and the Earth must be involved in this equation. But what about the distance? Well, he kind of reasoned that it must be in the denominator because if it's anywhere else, the force of gravity would increase. If it's, say, in the numerator, it increased with increasing distance, which makes no sense. Intuitively, you can figure out that if you put it in the denominator, that means that the influence of gravity will diminish as it gets farther away from us, which makes perfect sense. But why is it the second power? And how did he know it was the second power? Could have been the first power, could have been the third power, could have been 2.5, could have been 2 3/8, could have been almost any value, but he found out it was 2. And how did he do that? Well, part of it's the brilliance of Newton, but the other part is the fact that the moon is there and a few other characteristics. Let me look at this. There is a figure. It was taken by a Voyager spacecraft. It shows both the moon and the Earth and the moon together, and it's really to scale. That's how much larger the Earth is than the moon. Though they did have to brighten the moon up a little bit because you see the moon doesn't reflect light nearly as well as the Earth does. The Earth has a lot of clouds, and they reflect very well, and the atmosphere does too. The moon lacks both of those. And by the way, the distance between them is greater than you think because there's a lot of scale in the direction of the screen. As it turns out, well, I'll tell you right now, the moon is 60 times farther away from the Earth than the Earth's radius is. So if you take the radius, that'd be half the Earth's diameter, it would be 30 diameters away. So this thing, maybe the moon's a little closer to you than the Earth is, and so you're kind of foreshortening that distance. So it's 60 times, and that's significant. That means when you're standing on the surface of the Earth, you are 60 times closer to the center of the Earth than the moon is. And remember, in gravity, it's the center-to-center distance that matters. Now, people are already measured, by the time of Newton, they'd already measured the acceleration of gravity on the surface of the Earth. It's 9.8 meters per second squared, or 32 feet per second squared, whichever unit you want to use. Now, Newton was able to develop his laws of motion, and from that, he was able to figure out a relationship between the orbital period and the distance of the moon to tell him how much acceleration was required to keep it in orbit. And when he did that, he found out that what he computed, what's necessary to keep the moon accelerating around the Earth every month was 1/3600th of the measured acceleration on the surface of the Earth. That is, on the Earth, we're accelerated towards the Earth's center 3,600 times more than the Moon is as it orbits around the Earth every month. Now look at these two numbers, 3,600 and 60. What's the relationship between those two? Well, it's a squared relationship. If you square 60, you get 3,600. And folks, that is how Sir Isaac Newton was able to figure out that the inverse square law of gravity. That's brilliant. If I lived to be 300 years old, I would have never thought of that. But now he pointed out to me, oh, that's obvious. Brilliant man. God made Newton, but he also made the moon. And the big thing he was looking at was trying to answer the question, age-old question since ancient times, what compelled the moon to go around the Earth every month? And he came up with that answer, which also gave the law of gravity, which then the rest is history because he wrote the Principia. Using this, we were able to then develop physics as we know it, and it gave us electricity, it gave us all sorts of other things that we wouldn't have had otherwise. So I thank the Lord that he made Newton, and I thank the Lord that he made the moon. And again, he didn't have to make the Earth with the moon, but he did. Again, maybe that's a coincidence, but how many coincidences are you allowed to have before you realize they're not coincidences at all? And then there's the Earth. And I would argue that the Earth is unique. This is one taken from space. I'm not sure exactly when, but it's showing you much of North America and some of Central and South America. And the Earth is unique in many ways. You see, it's got the right distance from the sun. If the Earth were a lot closer to the sun, we'd get more solar radiation, and the Earth would be very hot. Too hot for liquid water to exist. And we all know that liquid water is essential for life. You can't have life without water. But if you're too far away, if you move it out, say to where Mars is, it's too cold and all the water will freeze out as ice. So you've got a narrow range around a sun, or star like the sun, where we call the habitable zone or the Goldilocks zone. If a planet is in that region, it might actually be able to sustain life. If you're outside of that range, it's not going to happen. And the Earth happens to be right in the sweet spot of all of this. But there's more to it than just simply being the right distance from the sun, because you see, the moon is about the same distance from the sun as the Earth is, and it's dead as a doornail. There's some things wrong with the moon. It doesn't have the right size and doesn't have the right composition. It's too small, its gravity is too weak. Its surface gravity on the moon is only 1/6 of what the Earth has, and so it can't hold on to an atmosphere. And an atmosphere is absolutely essential because we need something to breathe, we need something to provide pressure to keep our bodies together, and we need liquid water, which can't exist in a vacuum. So a lot of things coming together. The moon cannot do that. And the composition of the moon is a little wrong too. I won't go into that now. But just having an atmosphere isn't good enough. You need the right kind of atmosphere. And the right kind of atmosphere is a diatomic nitrogen-based atmosphere. Now, what do I mean by diatomic? Di means two, atomic means two atoms. So most of our atmosphere is made of molecules made of two atoms. For instance, the nitrogen, which is like 78% of the oxygen of the air around us, is N2, meaning it has two nitrogen atoms bonded together to give you a molecule of nitrogen. 21% of the atmosphere is diatomic oxygen, O2. Two oxygen atoms bonded together to make one molecule of oxygen. That's 99% of the atmosphere or more. Now, the remaining 1% has a number of other things, including polyatomics. These are molecules that have 3 or more atoms in them. Now, polyatomics, this is very important, are what we call greenhouse gases. Because they have 3 or more atoms together to make the molecules, they block infrared radiation, some better than others, but diatomics don't do that. Monatomic, single atoms like helium or krypton or xenon, they don't do this either. Only polyatomics do. Question, is the greenhouse effect good or bad? The answer is yes. You need a little bit, but not too much of those polyatomic gases. Why? Well, no matter where you live, if we didn't have a greenhouse effect, at least a small one occurring, no matter how hot it got in the daytime, like 110 degrees Fahrenheit, at night the temperature would plunge well below freezing every night because we wouldn't be able to hold in the heat stored up during the daytime. So a little bit of polyatomic is a good thing, but you can have too much of a good thing. Venus has too much of a good thing. It's got a very thick atmosphere, almost entirely carbon dioxide, which is a polyatomic gas, and it's like 900 degrees Fahrenheit day and night on that planet. Not a very good place. And so the atmosphere of the Earth is ideal. No other planet in the solar system has that kind of atmosphere. And then also, very important, is liquid water. Liquid water, as I already mentioned, is essential for life. But you know, water is not a rare commodity in the universe. When I say water, I'm talking about H2O. Let's don't talk about liquid H2O, which is AKA water. Let's talk about H2O, the molecule. It's either the second or probably the third most abundant molecule in the universe. Astronomers have found H2O all over the place, in space between the stars, atmospheres of stars, and on some of the bodies in the solar system and outside. The thing is, everywhere we've directly detected H2O, it's either solid or gas. We can infer that liquid H2O, aka water, exists in a few places, but we only infer that. We've never actually directly observed that. Because you see, liquid H2O is an extremely rare commodity, essential for life and found in abundance on the Earth. Which brings us to our next point, different atmospheres of planets, because that's fundamentally important. So here we have a figure I've put together with photographs of different planets. We've got the Earth, of course, here, and we have Venus. Notice the similarity in size. They're almost identical in size, with Venus being a little smaller. Over there is Mars, the next planet out. Notice how much smaller than it is than these. Got the Earth's moon there next to the Earth to scale. Here we have I believe this is Callisto, one of the Galilean satellites or moons of Jupiter. And on the far side there is one of the larger asteroids, a very tiny body. Now, some of these don't have atmospheres at all. The asteroid doesn't, these two natural satellites don't. Venus has too much atmosphere. Mars has too little atmosphere. And remember that Venus orbits closer to the sun than we do, so it's hotter, and Mars, it's cooler on each one of those. And so when we look at the Earth and compare them to others, I'm reminded of the rhyme of the ancient mariner. I have to think water, water everywhere, but not a drop to drink. Not on the moon, not on Venus, not on Mars, not on Callisto. Only on the Earth in the solar system do we find liquid water, and it's in abundance. I don't think that's a coincidence. But hold on, we're not done yet. We want to compare to other worlds as well. Venus, as I said, too hot. Mars is too cold, and the moon is dead. Only the Earth is just right. But beyond that, we also have many discovered planets elsewhere. We call them extrasolar planets, or more often we call them exoplanets. Exoplanets are planets orbiting other stars. And we've had a real breakthrough in this in the last 30 years. Around 1995 or so, the first planets around other stars were discovered. And we found a lot of these. We have different techniques for finding these things. One of these is the Kepler mission that was sent up a few years ago. We got another one going now, doing a similar sort of thing from space, looking for planets orbiting around other stars. We have TESS, the Transiting Exoplanet Survey Satellite. And I use the word transit there, and you may wonder what a transit is. It's sort of like an eclipse. When you have a larger appearing body being eclipsed by a smaller appearing body, we call that a transit. It's not technically an eclipse when that happens. And I have a little diagram here to illustrate this. Let's suppose that we're looking at a planet, a star off in the distance. Here the yellow circle represents a star, and it has a planet, much smaller of course, orbiting around it, indicated by the red dot. And we happen to be looking at this star near the plane of that orbit. It doesn't have to be exactly in the plane, like right in the middle here. It can be tilted a little bit, but if it's tilted much, there won't be a planet passing in front of it. We won't get a transit, as it were. Now, most of the time, as it orbits around, it's going to be out here, and no big deal. But once each orbit the planet will pass in front of the star, and as it does, it will block off a little bit of that star. And stars are bright. If you knock off a little bit of its luminous surface, you're going to cause it to eclipse and be a little fainter. And this is what the light curve down below is showing you. It says time horizontally and brightness here. And notice when the planet starts to pass in front of the star, the light dips down and then recovers like that. And then a next orbit will do it again. Now suppose that you were on a planet orbiting a star some distance away, maybe 100 light years away, and you're point your telescope towards the sun, and you happen to lie near that orbital plane of the Earth. Well, once a year, for 8 hours, the Earth will pass in front of the star, maybe a little less than 8 hours, depending on the tilt of the orbit, and it will dim the sun by 1 part in 10,000. That's just 1/100th of 1% in dimming. Fortunately, today, we have the ability to measure 1 part in 1,000,000. So if we had our technology on another planet orbiting another star, looking back at the Earth and saw it transit, we could easily pick up the Earth this way. We've done this for numerous planets orbiting other stars. And here, that was the theoretical what it looked like. Here is actual data. You see the scattering of data like this? That tells you how accurately we're measuring it. And then it dims down and recovers and goes on its merry way. Then it comes back an orbital period later and does it all over again. And by making these observations, getting this light curve, we can, by the shapes and depths of the curves, we can figure out a few of the basic properties of that planet. How many exoplanets do we have now? It just started happening in the mid-90s. For the first time, the technology had reached that point we could do that. Well, today, we now have over 6,000 known exoplanets. 6,000. Now, if you would have asked people 30 years ago, scientists 30 years ago, once we get 6,000 exoplanets, how many would be Earth-like? I think most scientists would have said, oh, hundreds would be. Hundreds of them would be. Now, why do we look for exoplanets? Why is that important? Well, they want to prove that planets are common in the universe. And then they want to prove that solar systems, or if you will, planetary systems, are common in the universe. Then they want to prove that Earth-like planets are common in the universe. And if you have Earth-like planets with liquid water and all this sort of thing, then that proves that life is common in the universe. And what's really going on here is that evolutionary scientists, they want to make sure that we have arguments to show that life is common in the universe, because they believe if life is common in the universe, then maybe there's not a creator. Life just happens on planets wherever the conditions happen to be right. Well, if that's the case, then what does it mean if Earth-like planets are not common? It means that life is not common. And if life is common, or if you will, rare, not to the point of being unique to the Earth, doesn't that kind of suggest creation at this point? It's kind of a division between the two. It's a test, crucial test between the two. If life is common in the universe, or maybe common in the universe, that kind of, if that proves that evolution's true and there's no creator, then the lack of life elsewhere would seem to disprove that idea, which proves there must be a creator. You can't have it both ways. You can't say, well both the atheistic theory of the origin of life can explain both of these. No, that's not how science works. You need a crucial experiment. It either proves one thing or the other, or it proves nothing. So what have we found so far? Well, we found that planets are common. With 6,000 exoplanets, we're only finding a fraction of those because many of them, the orbits are not tilted properly for us to be able to see transits at all. So there must be a huge number of planets out there. And we're also finding that planetary systems may be common. We found several stars now with several planets orbiting around them. What about Earth-like planets? Well, as it turns out, Earth-like planets are not common. Remember I said if you would have asked scientists 30 years ago how many exoplanets would be Earth-like when we found 6,000 of them, they would have said hundreds probably. Well, we haven't found any yet. Occasionally there's a news report saying they found an Earth-like planet, but usually in a matter of minutes I can find several things wrong with these planets which tell me they're not Earth-like at all. And the evidence is getting stronger every day that Earth-like planets are rare to the point of, well, we've not seen any. So therefore, perhaps the Earth is unique. Now, you might say, well, we just need to keep looking and find out more. That's true, but when we have enough data, You can always collect more data. You can always find more exoplanets. At some point, you have to stop, at least temporarily, and say, we can make a conclusion based on what we have right now. And my conclusion I reach is that we have no habitable planets yet. Now, somebody might say, well, wait a minute, the data are not all in. Again, the data are never all in. We should make a conclusion based on the data we now have, not based on the data we might have next year, next month, 10 years from now. We need to make that claim, that conclusion now. So I'm of the opinion that the solar system is unique and the Earth is unique with respect to life. Well, kind of wrapping this up, again, how many coincidences can you have and not have? Realize they're not coincidences at all. Wrapping this up, there's a thing called the anthropic principle, defined by Brandon Carter, I believe, in 1973. And what he noticed is that there were a number of coincidences about the universe that seemed to make the universe ideally suited for life. That is, if the universe were any different, we would not be here contemplating this question. What a strange universe we live in. It just happens to be good for our existence. And people have wrestled with this quite a bit over the years. In fact, I've argued here that the Earth is unique, that the universe is also unique. I could talk about the interesting properties of the universe that with any other way we wouldn't be here. So much so that back probably around 1990 or thereabouts, two astronomers or scientists wrote, Barrow and Tipler, they wrote a book called The Anthropic Principle. And this book is over 1,000 pages long. It gives a history of the anthropic principle. It gives different versions of it throughout time, and they critique the different ideas about it and discuss it. A very exhaustive treatment. But when they got done, they got to the conclusion, they said, yes, the universe appears to be designed, but it's just an appearance of design. I find, folks, that's remarkable. They have in their hands all the evidence to indicate that the universe seems to be ideally suited for us. And it gets back to my opening comments, the fact that design is not a conclusive argument, because if people don't want to believe, they're going to make up something to try to explain it away. They're simply saying the universe appears to be designed, but it really isn't. So the issue here about design usually comes down to a heart issue. It's not a head issue. These are intelligent people, but they refuse to make the right conclusion based upon the data because it conflicts with their worldview. Their worldview is driven more by their heart than by their heads, because you see, if there is a creator, if he made us, then he has a claim upon us. He can expect certain activities and behaviors from us and certain responsibility and accountabilities from us. But, you know, in our natural state, as the scriptures talk about, we're in rebellion against God. And we realize that we don't want God. It's that tough of an issue, heart, not a head. And people are trying to come up with ways to explain away the data because of this. But ultimately, we do know, as according to Romans 1, that there is a creator, and we deny that knowledge within us. So I think design is an important argument. I'm trying to make that case for people. I pray and I hope that if you're watching and listening, you too will have a change of heart in all this matter. Thank you for watching.